So today we have really exciting 3 separate talks with 3 separate speakers. And how it's going to go is each speaker has like a 15-minute talk, and they will give their talk. If you have questions in the meantime as they're presenting, feel free to use the chat at any time, write them there. But at the end of the talk, we'll get to the questions. And then so after the 15 minutes, we'll get to the questions, and then we'll take a short few-minute break so you can go grab water, and then we'll go to the second one and then the third one. That's the deal. If you have any technical issues, anything else, you should feel free to reach out to any of us with the name SITN on our Zoom names. Also, this is on Zoom and YouTube Live. So you can ask your questions both in the Zoom chat, which you can reach from like below the screen, and on YouTube Live, it's usually on the right-hand side. So you can use both of them. We read both of them. We will look at all of those questions. And if you have Zoom issues, you can go to YouTube. You can do all those things. But yes, so tonight we have a space-themed series, 3 awesome talks, and I think Heng is going to get us started.
All right, thanks for the introduction and welcome everyone. We are 3 graduate students and postdoc from MIT. So you can see from my background, we are given a series of 3 talks featuring the spacecraft with superpower. So I'll get started with the research that's related to what I'm doing. The title is Imaging the X-ray Universe, where I'll give you a brief introduction to the X-ray telescopes, how it works and why do we care and what we can do with this. So in the next 15 minutes or so. To start, well, we can look at the background figures. They are showing the Orion Nebula, which is one of the closest star nursery. So where new stars are born in this cloud. The figure in the left is taken with telescopes as invisible light that our eyes can see. So these clouds are clouds of gas and dust, which is relatively lower in temperature. While when new stars are forming, the gas will contract and attract to each other. They'll become much denser and hotter. And then at some point, a little light will start to come out. It will also shining other types of light that we can see. For example, in this region enlarged, on the right, we see this little dots that are taken with X-ray telescopes. Those dots represent the new stars. And those are very important for us to understand how the stars are formed and other things like for the birth of the new stars. So in the next, I'll tell you how this is done and how we can do that. So X-ray, just like it's a little bit said earlier, is a form of light, just like visible light and like some other, it's relative to light. So light is both a wave and a particle. It has wavelength. So the longer the wavelength of a light is, the lower the energy or smaller the energy of the light particle it is. So visible light is sitting right at the center of the spectrum. It has a wavelength roughly on the order of a cell, like single cell animal is on that order. Well, longer than that, we have microwave and radio. For example, the microwaves you're using in your home, it has a wavelength like on the order of millimeter. Well, on the shorter end, so that's where X-rays, gamma rays, and high energy radiation laser. So X-ray is much higher in energy and much shorter in terms of wavelengths on the order of atom size. So we didn't know that until 1895. That's a little bit more than 100 years ago. It's discovered by accident by a German scientist, Röntgen. He discovered this and he took this image, the first X-ray image ever for his wife's hand. You can see the bones. That's because our flesh and tissues are mostly transparent to X-rays, and our bones can partially absorb it. So he can. So that's why the bones are dark. You can also see the ring on her hand. So that's basically because X-rays are really high energy, and it interact with materials really strongly. So that property can be used in many medical applications or material analysis. For example, you can look at inside the human body to see if there's some abnormal like behavior in our body, like that's called a CT. You can also look at the X-ray luggage screening at airport security. That's basically you can look inside things. The short wavelengths can also be used to look at the structure of very small materials like protein. So those are applications. Well, now we're talking about astronomy. So X-ray astronomy is a space science. Why is it? If we draw a line representing the Earth's atmosphere, and in the bottom, we can plot our light from now I flipped it, so the left hand is shorter wavelengths and right hand is longer wavelength. So visible light is basically right at the center of the spectrum, and visible light can pass through our atmosphere. So we can see things, that's basically. A little bit longer than that, there's infrared. However, infrared are mostly blocked by the Earth's atmosphere. So infrared telescopes also are in space. Well, even longer, the radio waves, what radio waves can pass through. So maybe you've seen those like very big dish like telescopes. So those are trying to detect radio waves. On the very short end, we have this gamma rays and X-rays or ultraviolet. So they're all blocked by the Earth's atmosphere. So to detect those, we have to put the X-ray telescopes up in the sky. That's why it's a space science. We want to detect things from above the Earth's atmosphere from these astronomical objects. And this is good. Well, the Earth's atmosphere can protect us from these very high energy radiations. That's good for life on Earth. But if we want to do astronomy, then we have to figure out a way to put things on top. The next question is, why do we even care about that, and why is it important? There are a number of reasons. These very high energy phenomena that we didn't know it happened in the universe until like 100 years ago, but now we see it's really important for understanding for the dynamics of the universe. If you want to know how the universe works, so we need to look at the spectrum. It comes from very high temperature gas, very compact stars where stars are so dense, and even in the interstellar medium, like the space between stars are not so empty that we know. It also comes from many drastic and abrupt events, like the explosion of a supernova. Maybe you've heard of it, or maybe not. So those are very abrupt events and that can be detectable in many wavelengths. But each type of astronomy is just a window into the different aspects of the objects. It's like people can look at the elephants from many different angles. You can look at the ear, you can look at the tail, you can look at the body. But all these, we need all of those views to help us understand the whole elephant. So now we can look back at the picture at the beginning, as I a little bit illustrated. So you can see, so this is the visible light plus the X-ray, or this is the X-ray. So they are shown very distinct characters of the same part of the universe. But those are very important for us to together understand how stars are formed, etc. So the early X-ray observations, it didn't start until like 60 or 70 years ago. We have to put these observatories above the Earth's atmosphere through rockets or balloons or small satellites. So the picture on the left is a sounding rocket that's launched in 1962. So the rocket carries some instrument. So it's launched to stay on top of the atmosphere for just 5 minutes or so, where it try to detect the X-ray from outside our Earth. Then in 1970s, first Earth orbiting satellite for X-ray astronomy was launched. And in this figure, the lady on the left, she was the first woman to get the engineer degree in NASA, I think. So it's really kind of important thing at that time. Then in 1978, Einstein Observatory, that's the first fully imaging X-ray telescope, is launched on a satellite. So before that, we're only basically collecting photons, like we're collecting light, but not really looking at the stars or objects. But from this point out, that's where we start to really try to obtain an image of the objects. So it's like when you wake up in the morning, before you open your eyes, you can feel, oh, there's a light coming in. You see a little bit, but you can't really see anything until then you fully open your eyes, and then your pupil can start to image things and tell you, oh, that's your cat that's coming through. It's like that. So how do we image this invisible light? Because our eyes cannot see that. We build instruments. Maybe you think it's like the lens or your camera to do the same, where light comes through in form, like form image using this type of setup. However, this is wrong for X-ray. And the reason for that is because, like I said before, X-ray is very high energy. So it will penetrate most of the materials like at this angle. So the right way to do that is to come in a very shallow incidence angle, like the one shown on the right. So it comes in from the left and reflect a very shallow incidence angles. And early scientists have designed some telescope using this type of design, but he proved that you need 2 sets of mirrors to obtain better image quality. And now we put many layers of this thin mirrors to basically just increase the number of photons or increase the amount of light that we can collect, so the image will look brighter at the focusing plane. And for an imaging system like this, it's really important to know the resolution. That's basically how we can resolve 2 objects from very far away. So the further away or the smaller thing you can resolve these 2, the better the resolution is. And the best one that we have achieved so far for X-ray telescope is with Chandra, with only a 0.5 arc second. So arc second is 1/3600th of a degree. So it's basically, it's very small angle. That means we can resolve 2.5 feet from a distance like New York to Boston. So that's the very best vision. And to do that, you need this very specific designed telescope mirrors. And what do they look like? For example, on the left is a Chandra that I said that has a best vision so far. It was launched in 1999, and it has 4 sets of very thick mirror shells. Like those are illustrated here. So of course, these are taken before it's really launched. It's taken on Earth. So compared to the person, this is 1.5 meters or so. The light X-ray will come through this way, and they focus 10 meters further away. The one on the right is from a more recent telescope. It's called New Star. It's also a little bit smaller, but the mirrors, you can see this cross-section image where there are much more mirror shells, but they're also much thinner. And the light will come in through this, basically, and reflect it twice, and got image also 70 meters away. Not 70, misspoke. So the actual mirror fabrication process is a very involved process. So maybe with the details, but we'll start with the mirror shells. It needs to be perfect, and they somehow need to be aligned and to be mounted, then aligned to achieve the final telescope mirror assembly. And my research is really just on this first part. Is basically, how do we make good X-ray mirrors? And trust me, it's not a very easy research topic. Many people are working on the different aspects of this. So for future telescope, we want to obtain very thin, but also very good quality mirrors. The mirror, it's basically only the eye of a telescope. It's a spacecraft. So the whole thing is a spacecraft. The mirror is only at the front of this spacecraft. And at the end, there's also the science instruments, basically the sitting and the imaging plane, where it will detect and achieve like image of like the science characteristics that people are interested in and talk back to the Earth while it's orbiting on Earth, about the Earth. There are also some different flavors of the design for telescopes. For example, apart from Chandra, there's also New Star has much longer focal distance. There's also XM Newton. This is a European mission. It has 3 different telescopes, like 3-eyed spacecraft. Each of the eye serve a different purposes. Well, there's also a very different sort of design. Is called nicer. Is sitting on top of the International Space Station. So for future telescopes, currently there is a concept called LINX that's founded for study by NASA. It will try to achieve larger and sharper and clearer. It's basically going to be better eyes for the telescope. And it will be put at the Sun-Earth L2 Lagrangian point. I'll not really talk too much about that, but please see Jim's talk next, and he'll probably tell you a little bit more about what the Lagrange point is. So what do we try to achieve with this kind of telescopes? Well, maybe some of you will remember this image on the left from a year ago, 2 years ago. It's called the first ever black hole image, which is true. It's the first image where we have taken with in the telescopes. So it's called the Event Horizon Telescope. It's basically all the radio wave telescopes on the Earth is trying to obtain the image of the black hole at the center of the galaxy M87. At the same time, X-ray telescopes like the Chandra were also looking at the same thing, but it's looking at much larger, like big scale. So this image, so this white one is from the center of those, but the black hole is basically as small as the center, like a little cross mark. It's so small comparable. But why do we, what are we trying to do? Why do we want to use both of them? Well, for the X-ray images can see a jet, and that jet comes from the black hole. So that will tell us something about how the black hole is spinning, and also the other characteristics of the black hole. That's really important. So you can think of this as, this is a trumpet. So the black hole taken with EHT is looking at the mouthpiece of the sound you just made. But X-ray telescopes are looking at much bigger scales, how the sound wave travels down the hall, the music hall, as it propagates. So the X-rays will help us understand these properties. So for future X-ray telescopes, we're trying to look at clearer images of this. And those are very important for understanding how the universe works, and how the end, like the death of these very heavy stars, how the like supermassive black holes are formed, etc. These kind of questions. So in summary, cosmic X-rays come from very high energy objects. They play a very crucial roles in the dynamics of the universe. And X-ray telescopes are spacecrafts. They have to stay above the Earth's atmosphere via rockets, balloons, or satellites. And the mirrors to image X-rays require a very specific design, and they're hard to make. This one area that my research is on. And the future X-ray telescope will be larger, clearer, and sharper above all. So that is the end of my talk. Thank you so much. I hope you enjoy this little introduction to X-ray telescopes. So if you have any questions, please let me know.
Thank you so much, Heng. That was fascinating. We already have a few questions, but please type your questions in the chat, either on Zoom or YouTube. I'll get to the first one. What are the mirrors made of, and what are they coated with?
Oh, that's a really very good question. So original, for Chandra, the mirrors are made with a type of ceramic called zero-dur. So the way they are doing is they basically grind and polish it, but you can't really grind and polish to achieve a very thin thickness. So that's why the mirrors are so thick, if you remember from previous image. The later ones, so the later ones, the new stars are glass, emitted glass. It's coated with some high reflective coatings, like iridium gold. I don't think they use iridium exactly, but the coating for X-ray mirrors are also very specifically designed to enhance the reflection. And this new mirror, or new mirror technology that people are working on, or our groups is working on, is use silicon. So it will also be coated with multi-layer coating. Specifically, yeah, that's a very good question.
Great, thanks. And we have another question from our YouTube audience, which is what makes the Lynx a different telescope? So does it have a new kind of mirror or many mirrors?
Oh yeah, both. So both the sort of the eye part of the telescope, the mirrors will be good. It will be thin and has to have the same good resolution as a Chandra, but it also will be much lighter and much thinner. So more layers and more light can be collected. There are also a lot of developments in the science instruments, like in the detectors, basically how you can collect those lights, and also some other like science instruments will be much better. So in general, will be maintain the same resolution but have some other like capabilities. I leave that out in basically every criteria.
All right, we have one more question, I think, and that's, do these telescopes take images as they're moving, and are there any challenges with that, or do they like stop in mid-space and take photos?
So that's also a very good point. Very good question. Oh, the audience are making very good questions. So they will stay at Sun Earth L2. So this new one will stay at Sun Earth L2 Lagrange point, so it's more stable. It will look at one object for some time and collect the data. It will probably rotate a different angle and look at something else, but it's relatively stable at this at this L2 point. The other the Chandra one, it does rotate around the Earth. So I don't do that part of the research, but I'm pretty sure they you can't really collect the data while it's moving like all the way. So the scientists must have ways to deal with that part. Well, that's a good question.
Awesome.
All right. Hello, everyone. Good evening, and thank you for coming to this talk tonight. So I'll be bringing up the second segment on my work, both as a graduate student and now as a postdoctoral researcher on small satellites with laser vision that can act as eye doctors for giant telescopes. So I'll first begin with a brief orientation on my place in space telescopes. This is a picture of Edwin Hubble, the astronomer after whom the Hubble Space Telescope is named. But my job is not his job. My job is more like these gentlemen here who are building the telescope that Dr. Hubble would use to observe the universe. So I'm not an astronomer, I'm an aerospace engineer, but I work with astronomers as part of my job. But much like most of you, I mostly see astronomy as producing pretty images. I don't study them for a living. So with that disclaimer out of the way, probably the first question raised by my talk title is, why do telescopes need eye doctors? And the short answer is that they need eye doctors the same reason that I go to the eye doctor, because my vision's blurry and I want to see better. As an example, this image here is the M100 galaxy as seen through the Hubble Space Telescope in 1993. And to my layman's eyes, it looks rather pretty, but to the astronomer's eyes, this was a great disappointment. As you may recall, the Hubble Space Telescope's primary mirror was not manufactured correctly. Fortunately, the HST was designed with upgradability in mind, and so NASA was able to send up a mission to install a set of corrective optics, like eyeglasses, and they were able to bring the telescope back into focus. And so this is an image of the same galaxy taken after that servicing mission. And now we can see not only that it's a spiral galaxy, but we can see the structure and the clouds of within the arms, and even into a little bit into the core of the galaxy, the details that were blurred out of recognition before. And an interesting aside, the astronaut who's standing upright in this image in the middle is Jeff Hoffman. He's now a professor at MIT, and it was taking his course that led me to be an aerospace engineer today. So the Hubble Space Telescope was a very successful mission. It still is a very successful mission, but it is more than 30 years old. We've learned a lot about how to build cameras and mirrors and things since then. And astronomers are always ever more ambitious. They're always wanting to see objects further away that are fainter and with more detail than ever before. And so the way to do that is to build bigger telescopes. So this is a figure showing the primary mirror of the Hubble Space Telescope, the silver disc next to a person. It's about 8 feet across. And then next to it is the primary mirror of the James Webb Space Telescope, which is now fully constructed and awaiting launch. The planned launch date is Halloween later this year. It's going to be 2.5 times the size of the Hubble Space Telescope's mirror, which is in fact so large they can't make it and launch it in a single piece. It has to be made out of those hexagonal segments. And it's going to, so that will give it the greater light collecting area. It will give it a higher resolution. It's also coated with gold because the JWST's particular mission is to study in the infrared. So where Heng's telescopes are studying very high energy forms of radiation, JWST will have to study very low energy forms of radiation to see the very dimmest, faintest, and coolest objects in the universe. Ones that are very far away and that are very old from the earliest ages of the universe. But even as impressive as JWST will be, there are still more ambitions of the astronomical community that it won't be able to satisfy. In particular, the next giant leap in telescope design is to be able to observe not just stars and galaxies and nebulas, but individual planets. And so to achieve that, NASA engineers and scientists have been designing an even bigger telescope called LUVOIR, the Large Ultraviolet Optical Infrared Surveyor. So it will, like Hubble, it will be able to see not just the infrared, but visible and ultraviolet light as well, except it will be about 5 times the size of the Hubble Space Telescope, which will mean that it can take images in a day that would take the Hubble the greater part of a month to capture. And that means that it'll be able to zoom all the way in and it'll be able to see individual planets around other stars. This image on the left is a simulation of what this telescope might see if it were at another star looking at our solar system. And we want to be able to take pictures like this of other stars. Unfortunately, as these telescopes, as James Webb has grown in capability over Hubble, so too has its budget grown. When the Hubble Space Telescope's manufacturing error was discovered, it was called the $1.6 billion blunder. Meanwhile, the James Webb Space Telescope has yet to launch, and it's on track to cost $10 billion by the time it's finished. And so the concern is, why has that cost grown so much? And how do we prevent that kind of growth from occurring in the advancement from JWST to LUVOIR? And the reason that JWST costs so much more than Hubble did is in part because it's bigger and more complex, but a lot of it has to do with where the James Webb Space Telescope is going. So I'll give you a brief tour of our piece of the solar system and show you that difference. So here's Earth, population us, and the gold circle around it is the orbit of the Hubble Space Telescope. It's at an altitude of 340 miles. And if that doesn't sound like a very long distance to you, you're right. It's not very far at all. So I got my degrees at MIT. I'm still an employee of MIT, but I'm actually living right now near Washington, D.C. And there is a longer distance between me and MIT than there is between the Hubble Space Telescope and the Earth. Of course, I have it a little easier in that I can just sit still and stay where I am, whereas the Hubble Space Telescope had to be accelerated to over 17,000 miles per hour, fast enough to go around the world in 90 minutes in order to not crash back to Earth. But this kind of an orbit, this low Earth orbit, is not suitable for the James Webb Space Telescope. Because in just the same way that our eyes are blinded by bright lights, the James Webb Space Telescope will be blinded by sources of heat. And even on the night side of the Earth, there's enough heat being radiated from the Earth's surface that it would completely scramble JWST sensors. We have to send it very far away. So let's zoom out for a moment. So there's the Earth on the left side of the screen, and the moon on the right. It's about 250,000 miles away, or the equivalent of about 8 laps around the Earth. But even the moon, just like the Earth, the moon absorbs heat from the sun and it emits it. And so the moon is not suitable an environment for the James Webb Space Telescope either. So we have to go a little bit further. There's the Earth and the moon. You might be able to just see the moon as a little speck on your screen now. But the place that we're sending the James Webb Space Telescope will go is an invisible point in space called L2. That's a point where the orbital motion and gravity of the sun and the Earth cancel out. So it's a great place to send a telescope to keep it very cool and very still. And it's the same reason that Lynx is going there, and LUVOIR, and several other space telescopes before and since. But it's really not a great place to send a rescue mission. It's further away from the Earth than any human has ever been, and there is literally nothing for 1,000,000 miles in any direction. So that means that the James Webb Space Telescope had to be tested to excruciating detail because there is no rescue mission to come for it. So it has to work the first time, every time, and any little hiccup means that large parts of it had to be rebuilt and then retested all over again. And so that added years onto the schedule and billions of dollars onto the budget. Although, before I move on too far, I should stop by saying that the Earth to L2 distance, yeah, 1,000,000 miles, that sounds like a long distance. Yes, it is, but it's also really not very far at all on the scale of the solar system. So there's Earth and L2, they're now right next to each other on this scale. And yes, for those curious, there is an L1 on the inside of the Earth. But you can see the distances from Earth compared to to L2 is only a tiny fraction of the distances to Mars or the other planets. But that's a topic for Allegra's talk in a few minutes. So we'll zoom back into L2. So given that this isolated environment is the cause of so many woes for the James Webb Space Telescope, the purpose of my research is to say, what if instead of sending a telescope all by its lonesome into this isolated, cold depth of space, what if we sent a companion satellite with laser vision that could illuminate the telescope and act like an eye chart to give it the information to rescue itself, rather than demanding that we either be ready to send a mission after it or that we build it to perfection first. This is not a new idea to astronomy. They call it adaptive optics. For years and years now, telescopes have been shining lasers up into the upper atmosphere and measuring how that laser light gets distorted on the way down. Then they can change the shape of a mirror inside the telescope to cancel out that distortion and take the twinkle twinkle out of the little stars so that we can see them for what they are. But this technique has been highly successful on Earth, but it does have its limitations, both for space telescopes, there's no atmosphere to shine a laser into, and even on ground-based telescopes, even though that laser beam may look very straight on that image, to an astronomer's perspective, it spreads out quite a bit wider than a star. So rather than producing a sharp point up in the sky, the way that a star is, it's more like a fuzzy glowing blob in the upper atmosphere. So it's a bit like going to the eye doctor and using an eye chart that's misprinted. It's better than nothing, but there's still a lot of performance that's left to be captured. And so that's one way that, even though the space telescope is only to be launched in the relatively distant future, we can still make use of laser guide stars in space today to benefit astronomy missions that are already ongoing. So in conclusion, to take better images of the universe, we need to build bigger telescopes. And to help make take those telescopes out of the world of the impossible into the world of the merely difficult, we can use small satellites with lasers to help keep them in focus. And we're studying and testing these technologies in precursor missions today so that we can use them in the major flagship missions of tomorrow. Thank you. I'll take any questions at this time.
Thank you so much, Jim. That was super exciting. So please type your questions in the chat. We already have a few coming. I'll read the first one. Do we only need to make massive telescopes in space, or are there massive telescopes that live on Earth?
There are large telescopes that live on Earth as well as in space. And for the same reasons, a bigger telescope means that you can collect more light in the same amount of time, and you can also focus it more sharply. So there are actually larger telescopes now on construction, under construction on the ground. So I believe I actually have a backup slide. So again, here's Hubble, James Webb, LUVOIR. This outline represents the represents the primary mirror of the extremely large telescope, which is under construction in South America right now. You can see it costs as a project about as much as the Hubble Space Telescope, even though it's much bigger because we don't have to send it up into space. But the downside of ground-based telescopes is that, as Heng said, there are only so many colors of light that come down through the atmosphere. So the ultraviolet and infrared that LUVOIR will be able to see they don't come through to the ground for the ELT to see them. So there are always trade-offs to be made. And that's kind of my job as an aerospace engineer, is to work with the astronomers and figure out what's the best way to get what they want without breaking budgets.
That's great. Thanks, Jim. One other question related. Why do we need one big telescope instead of a bunch of little ones?
There are different missions that are served by the different kinds of telescopes. So having one big telescope means that you can collect a lot of light in a hurry. So especially for that exoplanet imaging kind of mission, where planets don't stand still. So if you take too long to try to image it, you won't see a planet. You'll see, maybe if you're lucky, you'll see a smear that it makes around the star. So bigger is better for that reason. On the other hand, there is also something to be said for having lots of small telescopes. So that's actually another project that I'm working on at MIT to have, because these big telescopes, they're wonderful instruments, but they can only look in one direction at a time. And so that means that you basically have to schedule in advance everything that it does, and there's only a limited amount of flexibility to try to catch sudden transient events. So there's a lot of work being done now to build constellations of small telescopes so that we can do interesting things like sit and stare at one star for months and months and months and months to try to catch planets that are too small or too close to be seen with other kinds of telescopes.
Really cool. Thanks. One other question. If we're sending a lot of telescopes to this L2 point, will it get crowded? Will a lot of telescopes being there heat up the area?
Not really. Unfortunately, I don't have a great chart showing you, but these telescopes don't just sit at that Lagrange point. Actually, but this is another picture. There are actually more Lagrange points than just L1 and L2, but it's not like there is a single point L2, but we don't actually have telescopes that just sit at that single point. They move on what's called a halo orbit around that point, which is itself a couple million miles across. That orbit is very large. So it's important to track objects there because we do want to keep them out of each other's line of sight, and especially if they're doing things like firing thrusters or what have you. But space is really, really big, and it's even bigger once you get away from Earth orbit.
Awesome. We have another question in the chat. I'll read it for you. It's from Katrina. Would it be possible to send smaller spacecraft to telescopes that already been launched, or would these eye doctor telescopes be launched together?
So the the space telescopes that are already in space don't have the adaptive optics technology in them. That's a relatively recent development, and these space telescopes take a long time to design and build. To put this in perspective, so the James Webb Space Telescope is launching later this year, but it was first designed in the 1990s with the intent to be launched in 2006. So it's had a very, very long development timeline, and so no space telescope currently on orbit would be able to make use of one of these eye doctor satellites. Although, as I said, there are a lot of ground-based telescopes that have that technology. So one of the projects that I'm working on is to use them as a test bed. So to launch these laser satellites into space to use with telescopes that are already built on the ground. And then that will prove that the technology works. And then it can be included in the development plan for next generation space telescopes.
Awesome. That's super cool. Another question is, what is it like to work with astronomers? Are there any disputes between different astronomers on what's a good image?
Not really on what's a good image, but on what's the most important thing to image. Yes, there's only so many hours in the schedule for a space telescope mission. And there are also trade-offs to be made on the design side as well. So for example, my advisor, Professor Carrie Cahoy, is on the Science and Technology Definition team of the Nancy Grace Roman Space Telescope, which is currently in its design phase to be built and launched in the late 2020s. And one of the big design trades they're making is, do we try to build the Roman Space Telescope out of a leftover spy satellite, which is free, or do we want to build our own telescope, which is not free, but we'll be able to make it exactly the way we want it, because the spy telescope was made to look at the Earth, and so it has certain design compromises that went into it because to serve that mission. And so it's a question of what are we willing to compromise? Are we willing to compromise on the performance in order to get better detectors or a better launch or more lifespan out of it? Or do we try to push for the more astronomically ideal instrument? So it's a lot of fun to work with them, and it's a different kind of design challenge than a typical communication satellite or Earth observation satellite problems.
That's super cool. Thank you for sharing that. It's nice to hear that there's telescope thrift shops almost that you can harvest old ones, vintage.
Yeah, so the Hubble Space Telescope was in some degree built the way it was because it was based on a very long-lived platform of Earth observations by satellites. But that's why it has those big, you might see from some of its pictures, it's got these big cross-shaped marks over all the stars. That's because of the way it's built. And astronomers would really love to not have those if they can get away with it.
Thank you so much.
Awesome. Hello, everyone. My name is Allegra Farrar. I am a first-year graduate student at MIT. I'm in the Aeronautics and Astronautics department, and I am currently studying the problem of how are we going to get humans to Mars? Can we do it? And if so, how are we going to do it? So I'm going to talk a little bit about that today and give a little bit of background on my research and some of the stuff that I do with it. But for starters, I'm going to start by giving some sort of historical background, a little bit of context to get you understanding what this topic is all about, where we came from and where we're going with this. So it kind of all started with the Cold War back in 1955, which prompted the space race, particularly between the United States and the Soviet Union. And because we were in wartime, it was this big race to the finish. Who was going to get to space first? Who was going to occupy space first? And whoever occupied space first, what did that mean for the other side? And because of that, there was a great sense of urgency that came from it. But the Soviets were winning. They were winning very well. They started with sending Sputnik 1 up, which was the first satellite to orbit the Earth ever. But we did good. We came in right after them with the Explorer 1 that launched in 1958, and which was our American version of the first satellite that also orbited the Earth. But here comes the Soviets again. They sent the first man into space, Yuri Gagarin, and he was the first man to ever complete a full orbit around space. But a month later, we sent our first astronaut into space, who also completed one full orbit. So now we're at the point where the Soviet is winning every challenge up to date. And so the United States thrusted all of their resources, all of their money, all of their efforts and educational efforts and intellect behind getting to the moon. And we did it. We were able to get to the moon first. And we were the first humans to land on the moon as the United States. So now NASA is really put on the map as an organization that is doing this high profile, high stakes technology that are sending humans out into our solar system. So everyone's kind of looking at NASA like, okay, what you gonna do next? And NASA's next initiative was a program called the Space Shuttle. And the Space Shuttle was a reusable spacecraft that was used to send astronauts into space more frequently, sort of to keep space occupied and build up things such as the International Space Station and perform other initiatives as well. But we had a few tragedies along the way. In 1986, the Challenger exploded, which was the first major display of just how high stakes this challenge is. And it's nothing like flying in an airplane. And it was starting to become very normalized and as something that we could do often. But, you know, the Challenger explosion was sort of the first event that really struck a chord with that theory. And that was followed in 2003 by the Columbia explosion, which was another tragedy that took the lives of more astronauts. So we've had these issues, and now we're in present day and we're saying, okay, now we want to go to Mars. So that's a big jump. And as part of sort of explaining this jump and explaining how we can make this jump, that's where sort of the science and the research comes in. So now we're at the point of where do we go from here? I want to take a break and let you guys use the chat a bit. And I want you guys, if you feel comfortable, to put any assumptions that you might have when the words Mars comes to mind, or space exploration, or space shuttles. Feel free to use the chat and just plop the first thing that comes into your mind so we can sort of get everybody, make sure you guys are awake out there. Give you guys a few more seconds. And Lillian, if you can read the chat for me, because I can't really see it from my view, if there's anything in there.
Sure, yeah, we have an array of responses, everything from aliens and red planet to the fact that it's risky, potato farming, high risk, and not because they're easy, but because they're hard.
Yeah, nice Kennedy quote. Okay, so that's great. We're gonna circle back around to that a little later. But I kind of wanted to get you guys thinking of, you know, what are your initial preconceptions of what it means to go to Mars? So with that being said, we're gonna circle back to what Jim talked about in his talk. I kind of stole this from his line of images, and we're gonna talk about sort of this distance problem. So we're so far away from Mars. It's territory that we haven't even gone into and haven't even gotten close to. So what does that mean? And I liken this to something that I like to call the slingshot effect. And what I mean by the slingshot effect is if you've ever, when you were a kid, tried to annoy someone and you had a rubber band And if you pulled it back just a little bit, it might go somewhere, but it's not going to go far. But if you really reel it back and let that thing go, it can fly across the room and it can really hurt someone. So that tension that you experience with a rubber band is very similar to what we call a gravitational field. Now, every planet has a gravitational field, and it is a force that pulls objects into the center or onto the surface. And once you're within the influence of the gravitational field, then you experience that tension that we're talking about with this elastic band. So how does that come into play when we're talking about space travel? Well, the reason why this is important, especially with the work that I do, is because the farther out we are, so the more tension that we have, the faster in we're coming to whatever planet we're trying to get to. So if we are traveling from Earth to the moon, let's say, we're going to come in pretty fast, but relative to what we're dealing with, it's not super fast. But if we have a vehicle that's traveling all the way from Earth and trying to get to Mars, we're going to come in pretty hot, especially once we hit that gravitational field. And we're talking about doing this with people on board. So this is no small feat. This is something that we've never done before. And not only have we never done before, but this is unlike what we did with the Apollo missions, where we had all these resources and technologies to deal with. But we're going to have to develop even more stuff to solve this problem. So let's talk about that a bit more. So we have a few fundamental challenges when dealing with this whole distance issue, with this whole slingshot effect, all of that stuff that we're talking about. But before I go into that, if you've ever watched any space movie, any sci-fi movie, there's usually like a scene where you have the captain of the ship, the very valiant captain of the ship, who's navigating this complex force field, and he's dodging all these, all these terrains and doing all these complex maneuvers. And he ends up saving the day and getting everyone down to wherever they're trying to go safe. And while that makes for a great cinematic performance, it is very unrealistic. And here is why. When dealing with Mars, the Martian atmosphere is very thin. Now, what that means is that every planet has an atmosphere, and it's this layer of air, for lack of a better term, or air particles that exist above the surface that, like I said, contain air particles and things of that nature. And because our Martian atmosphere is so thin, we don't get that extensive drag force that we would get if we were coming in to Earth. So slowing our vehicle down becomes exponentially harder. The other challenge that we have is this high speed entry phenomenon, which is what we were talking about with the slingshot effect. And this sort of manifests into heat. So when we're traveling in fast, we create more friction around our vehicle, which manifests in very high heating levels. I'm talking about a magnitude of burning that could potentially burn up the spacecraft. So we're dealing with all of that. And then to add to all those challenges, we have the issue of an uncertain environment. So we don't know what we're going to encounter until we're there encountering it. And we have to be able to react to these challenges of what the atmosphere is going to be like once we get there in real time. And that's where I come in. So dealing with this complex environment, we need to find a way, especially when entering the atmosphere, of how to have a trajectory that is able to sense this environment, sense the challenges of this environment, and maneuver around those obstacles that persist from this complex environment. So to kind of give a visual aspect of it, we're going to try and put objects to a name to get you kind of understanding about what it is that I'm talking about here. Now, like I said, these are particles. These are on, nanoscales. You can't see them. But to try and visualize it, we're just going to throw some stuff up there just to kind of make it look like we have actual obstacles that we're trying to navigate around. Now, these particles, they can do whatever they want. They're stealthy little things, and they can interact with our vehicle in numerous types of ways. If you've been on an airplane, you know that when you're experiencing turbulence, you can't see anything. There's nothing hitting the space, there's nothing hitting the aircraft, but it manifests in a physical jolt or a slight drop when you're flying through the air. It's kind of similar when you're dealing with the atmosphere in a space shuttle coming down through the atmosphere. You have these air particles that are interacting with your spacecraft, and they're manifesting in physical results such as heat or navigation issues and things of that nature. So in order to deal with that, we have to find some sort of trajectory that allows us to avoid these as best as possible, so we're not doing undue stress on our vehicle and our passengers. So we need to, based off of where we're trying to land, we have a series of trajectories that we can take that maneuver us around these obstacles and get us to where we're going safe and sound. And that topic is something called trajectory optimization. It is a term based in autonomy, which autonomy is it's the concept of being able to navigate a vehicle without the need for human interaction, which is something that we're talking about here. Remember when I kind of mentioned that, you know, the cinematic performance of a captain maneuvering a spacecraft through all these obstacles is cute, but it's not realistic. The reason is that we're coming through this atmosphere on the order of seconds. So imagine trying to navigate something in about like 15 seconds worth. And also we're dealing with the astronauts within the vehicle are not going to be able to respond that quickly. It's like if someone threw you in, if you've ever been to a carnival and you see those things that spin you around and you're stuck up against the wall. It's like asking someone to then make you a sandwich while they're in that big drum spinning around and losing all their faculties. So this is why we need smart spacecraft. We need spacecraft that are able to act for themselves in the moment, since we cannot be there or we cannot use our astronauts to do that for them. So before I talk about like the specifics of trajectory optimization, we're gonna kind of play along with this thing with an analogy about basketball plays. So usually in basketball games, when it comes down to the wire and like you're down to like the 10-second or 15-second mark, and you need to make that basket, it's like a 1-point margin, and you need to make that basket to win the game. The coach comes in and gives you a play, gives the players a play. And they're expected to follow this playbook, but ultimately, once they're on the court and they're actually in the moment, they have to react to whatever their opponents are going to be doing. Because while they can try and predict what their opponents might do, they won't know until they're actually playing the game. And so that is the idea of needing trajectory optimization. We need some sort of way to provide the spacecraft with the computational infrastructure to maneuver around these obstacles, but ultimately we need the spacecraft to be able to determine in real time, in the moment, of how to navigate these obstacles in order to land our humans on Mars safely. And that is essentially what trajectory optimization is. And my role within all of this is I'm the coach. I'm the one that tells the spacecraft, okay, here's what you do, and here's what you can do. Here are your options. And here's how you can maneuver around your obstacles or your opponents in order to get down to the surface of Mars. But what we need the spacecraft to do as part of autonomy without our influence, because A, we're too far away on Earth to do anything, and B, our astronauts are dealing with too much, too fast to do anything. So we need the spacecraft to be able to sense the environment and navigate around those obstacles to land safely. And to kind of expand on this, we have this idea called funnel libraries. And what we're doing is we're creating this funnel of possibilities, building up the uncertainty around the trajectory in which we're traveling down to the surface of Mars, and giving our spacecraft options. You can do this amount of stuff within this lane, but you can't deviate from this lane. So we're giving our spacecraft a little bit more structure of how to deal with this uncertainty, but ultimately giving it options of ways to go in order to travel down to the surface of Mars. All right, so to bring this back down to Earth, sorry, no pun intended. I just want to wrap this up and kind of circle back to some of the stuff you guys put in the chat. to bring it all back home. But as I mentioned before, with the whole historical context and us being pushed into the space race because of the Cold War, we didn't have a structure. We didn't have a structure for space exploration. We were just kind of doing stuff in order to beat our opponents. And because of that, there were many things that we know now that we didn't know back then. And in order for us to be able to travel to a place like Mars, there has to be much more collaboration. There has to be much more, a much greater infrastructure in order for us to make this a possibility. So then that begs the question of, okay, well, why are we going there in the first place? We're curious. It's just that simple. We're curious. We want to know what's out there, and that's important too. There are great things that come from curiosity, and great inventions that come from curiosity. So that's a big motivator for us traveling to Mars. The other scientific motivators are that Mars is strikingly similar to Earth as a planet, and it has possibilities for us to understand not only our planet Earth and us for how to better treat our planet as it evolves, but also understand our solar system and the other planets within our solar system and how they're evolving and interacting with each other as well. And then, of course, we want to look for signs of life. I mean, aliens, and that's important too. Knowing what's out there, knowing who's out there, if there is anything, and that might not be a person, it might be, some microbiological organism that we spot, but we're looking for signs of life. But then there's indirect things that come from it. So space exploration in general is known to lead to discoveries that cross-pollinate across all the fields of science. Be it the Hubble telescope with breast cancer, figuring out how to better detect breast cancer from the accidents happening with the Hubble telescope to far beyond that. So some of the indirect reasons of just doing space exploration in general is that it makes us a better people. And we're able to do things that we want to do, but sometimes things that we never even thought we could do. And that's what results from so many minds working together to do such amazing things. And we can all benefit from wanting to make Earth a better place and collaborate on that and work together. So yeah, that kind of wraps it up. And with that, I will take any questions. Thank you for your time. I'm glad, we all could make it and learn a little bit more about how we do space.
Thank you so much, Allegra. So exciting. You left us on such a lovely, hopeful note. We already have some questions, but this is a prompt to everybody to type your questions in the chat if you have them, both on YouTube and Zoom. The first one is, why was the latest Mars mission so important? Was it to find out what's there and send back images to us?
Yeah, so the Perseverance rover that just landed about a month ago, it was big in many ways. And the biggest way I can sum it up is just that it gives us the prospect of doing more on Mars. It tested technologies for, such as like creating oxygen on Mars, and just the technologies for what I'm doing with being able to enter the atmosphere without, having all the complex challenges deteriorate our spacecraft. So it was beneficial in many ways. But there are very specific benefits that lead us into the possibility of being able to send humans up there eventually.
Yeah, thank you. This next question kind of relates to it. You mentioned a lot about like automating most of the processes. For what particular things are humans useful in a mission to Mars if they're completely incapacitated while they're being jostled around in these things?
Yeah, so humans are very important once you land. But unfortunately, because when that small moment of entering the atmosphere is like, it depends on the size of the spacecraft. It depends on, of course, a whole conundrum of things. But essentially, it's so short of a time span that just a human can't be involved. But that's just one small part of sending humans up there. You send humans up there, they're able to discover. You cannot beat a human mind. That's the moral of the story. But sometimes you can't involve a human in a certain in a certain task. But once we get on the planet and we land humans on the planet, they'll be able to do things that we can't do with rovers. that we can't do with just sending objects up there, because like I said, you can't beat a human mind, the intellect, the complex thinking it's very necessary in order to really discover what's out there on that planet.
Thank you.
Yeah.
Another question is, how is Mars so similar to Earth? What are the similarities?
So there's a few things. So one of which is the atmosphere. While it is different, the atmosphere is probably the most similar. The structure of the planet. So there's a lot of ways that it's very similar. Its core is similar to our core. So, understanding that there's scientists have a big stake in the claim for that. I'm an aerospace engineer, so I don't deal with the science part of it per se, but there are many reasons why Mars is similar to Earth. One of which being the atmosphere is something similar. The size of the planet, the fact that like you can even send humans up there with conditions not being completely devastating. So yeah.
Thank you. Oh, there's another question. How far are we in research towards this mission? How many years would you guess until humans can get to Mars?
Well, that's a tough one. It depends. So Mars comes around, I believe it's every 26 or 28 months. So we have like a 2-year and 2-month window for every time we can visit Mars. So that's number one. Number two, it all depends on how fast technology develops. Back when the Apollo missions were taking off, I mean, Kennedy projected that we'd do it at the end of the decade, but I mean, it was looking a little rough. I mean, there were many setbacks and challenges to doing that, and that was just the moon. I mean, we can see the moon every night, but something like Mars that is so far away, we got to make sure we dot our I's and cross our T's before we send people up there. So I don't know how long on the order of years it might be, but it's closer than we think. It's definitely a possibility at this point. It's not just an idea.
Awesome. I will post before we lose people, I will post a link to our feedback form in the chat. We'd love to hear from you. Tell us what else you're excited to hear about from the world of science, what you thought about today's talk, any issues you had. We'd love to hear from you. And I'm looking to see if we have any more questions.
We have one follow-up on that previous question, which was, what does it mean that Mars only comes along every 2 years? Is that just when it's closer?
Yes, it is. That's just when it's closer. So we want to shorten the time span of how long it takes to travel there, because right now, if when Mars is close, it takes about 7 months, I believe, to get there. And that's still a long time. But yeah, we want to be as close to Mars as possible. So yes, it's about closeness in orbit versus just it appearing. Yeah.